All right, let's get started. I did want to point out that in Canvas, there is a practice exam 3 posted, as well as I just published the solutions for it. So that you can just find that in the modules down closer to the bottom, but there it is right there. So if you're looking for more practice, there's more practice. That said, I didn't have a real agenda. Not light on? No, okay. I did not have a huge agenda for today other than kind of reviewing things that you might want to review because you all have well, most of you have an exam on Monday, right? Okay. This is not the right pen. So that said, I can take requests or I can look at problems from his very long list of practice problems that he posted. Um, but I guess I should start with, are there any things you all want to see specifically? Yeah, sure. Mine or his? Okay. 7. I have to go 5. Let me go grab it real quick. Sorry, wasn't prepared for mine. Let's see, where'd you go here? Yeah, good job, James. 1 second, let me open Canvas back up. Oh, or is it over there? No, I closed it right. Yeah, okay. No, it's right there. Haha. Okay, cool. Let me bring this back over to myself. Cool. All right, and you said number 7? It's totally fine. Assuming I know how to do it. Let's take a look. Sorry, one moment, please. 7. A and B. Okay, cool. Yeah, fair enough. So 7A. Find a unit vector. Not this pen. Go away, pen. Sorry, pen's thinner. Find a unit vector orthogonal, meaning perpendicular, to the very generic vector v equal to a comma b comma c. And I would say generally the following statement is true. If you're ever asked to find a unit vector that does a thing, first just find any old vector that does the thing. And then after you found a vector that does the thing it's trying to do, then divide it by its own magnitude to make a unit vector. So the unit vector part of it should be the last part you deal with. So there's a lot of options here. Whenever I think about trying to find a vector that's orthogonal to another vector, I'm trying to find a vector whose dot product with it's going to be 0. So if I call my other vector W, I know that now I don't want to do too much work here, really. Like you could make a whole vector and then dot them together and see what you need it to be. But really the idea here is the one we talked about before, which is make one of the components 0 and the other two non-zero ones, switch them from the original and change the sign of one of them. So an easy answer here before we make it a unit vector would be to say it's going to be, instead of A, B, C, B, A, 0, and make one of the B's or the A's negative. That vector certainly is orthogonal to V because V dotted with W is A times negative B plus B times A plus C times 0, which amounts to negative AB plus 0, which is 0. So that's the typical way you find any old vector orthogonal to another one. And then the next part would be to make it a unit vector, so divide it by its own magnitude. So then we're going to say that U, the unit vector, is W divided by the length of W, or the magnitude of W, which is going to be negative B, comma A, comma 0, divided by the square root of negative B squared plus A squared. You could write plus 0 squared, but that seems really unnecessary, but you could. And I would leave it like that. And then, actually, any questions about that before we do part 7B? So for 7B, the problem says the following. It says, using the vectors from problem 6A, find the projection of W onto V. So I'm going to write down first the projection. Now be careful here. Projection of W onto V means W is up here and V is down there. W is onto V. And then let's actually write down what W and V are from problem 6A. The vector V is the vector 0, 1, 2. The vector W is negative 2, 0, 4. Question. Are you given the projection formula on your formula sheet? Does the del give you a formula sheet? It looks like a no. No, not really. Okay. So we need to know this formula, right? Here's what I remember. I know I'm projecting onto V, so V is the one that shows up a bunch of times, and W only shows up once. So the projection of W onto V, I usually think of as W dot V divided by V dot V times V. You might think of it differently. You could also think of it as W dot V divided by the magnitude of V times V over the magnitude of V. Same difference. Any way you like to think of it. So I should point out, because I feel like this has come up a number of times, I've been helping people with stuff like this, is I would encourage you all to become very comfortable with the fact that a vector dotted with itself is equal to the magnitude of that vector squared. This comes up often. It's something you have to use. There's a problem about like showing that some vector bisects the angle of two other vectors, and you have to use this fact to prove that that thing is what it is supposed to be. So it comes up, but that's what's happening in the bottom here. This V dot V is really just the magnitude of V times the magnitude of V, which is the magnitude of V squared. In any event, let's calculate it. So W dot V is 0 plus 0 plus 8, right? 0 times negative 2 plus 1 times 0 plus 2 times 4. V dot V is 0 times 0 plus 1 times 1 plus 2 times 2, which is 0 squared plus 1 squared plus 2 squared. And finally, the vector V is the vector 0, 1, 2. So looks like we're getting 8 over 5 times the vector 0, 1, 2. I would probably leave it like that, but you can also choose to distribute the scalar multiple here and get 0, 8 over 5, 16 over 5. Either way should be acceptable. Cool. Another question someone could ask about this is, I would probably phrase it this way. So here's an add-on. Come on. This paper's bent. Okay, sorry. 7C. What is the length of this projection of W onto V? Well, it's kind of silly to take this vector and find its length, even though you could do it that way. So certainly one way of answering that question would be to say, well, it's just going to be the square root of 0 squared plus 8 over 5 squared plus 16 over 5 squared. But if you'd asked this question before you actually found the projection, they're really asking you just for the component of W onto V. And the component of W onto V is calculated as the dot product divided by the magnitude of V, which would be, again, the dot product was 8, and the magnitude of V was square root of 5? Yeah, square root of 5. Square root of 0 squared plus 1 squared plus 2 squared. Which should be the same as that. It should be. It looks a little suspect, to be honest. I'm not gonna lie. But it should be the same. I don't want to show they're the same though, because I'm looking at it here like this does not look like it's the same. Oh no, I think it is. It is the same. Let's show it since I seem to be confused about what that's it. So if we actually multiply this out, you get the square root of 8 squared is 64 over 25. Wow, I said 64 and I wrote 86. It's impressive. 64 over 25, and 16 squared is 256 over 25. Yeah, this does not look like it's going to come out the way I want it to, but let's see what happens. 256 plus 64 is 320. Oh, no, it's going to work out just fine. And 320 divided by 25, they both have a multiple of 5. 320 divided by 5 is not great. 80. Nope, that's not right. Gosh, my math today is not good. Divided by 5 is like dividing by 10 and then multiplying by 2. So it's 32 times 2, which is 64. Okay, that works out great. That's the square root of 64 over 5, which is 8 over the square root of 5. Woo! Okay, it works. One of them clearly looks nicer than the other one, but either way should be fine. Other specific questions I can address before I just start picking things at random. Actually, I do want to pick one thing at random, not at random, so not randomly at all, but come back here. Sorry, one moment. These are all over the place here. Ugh. There was one from his handout that I thought was kind of worth. So there's actually two here that are on his handout that I thought were kind of interesting. So one was the very first question, which was use a rotation matrix to rotate the vector 2, 5, doesn't really matter what the vector is, counterclockwise by the angle 3 pi over 4. And I'll be honest, I never remember what this matrix is exactly. I'm pretty sure I have a good idea of what it is. Do I have a good idea of what it is? Not really, actually. I know it's either, yeah, it's got to be that. It's cosine of the angle you want to use. And I don't remember if it's a positive sign here and a negative sign here, or a negative here and a positive there. But there's got to be one of the signs is supposed to be negative. How could we figure it out? That's a good question. How could we figure it out? Here's what we should do. So let's answer a different question completely. Let's say we want to rotate the vector 1, 0 by 90 degrees. Okay, so let's try putting the negative sign here because that's where I think it goes. So if I multiply this vector by this matrix, cosine of 90 degrees is 0, sine of 90 is 1, sine of 90 is 1, cosine of 90 is 0. If I multiply this vector, which is pointing that way, oh, and I should say by 90 degrees counterclockwise, the direction is important here. If I multiply that by 1, 0, let's see what we get. I get 0 times 1 plus negative 1 times 0. Cool. I get 1 times 1 plus 0 times 1. Also cool. That's exactly what I wanted. So the negative should go there, not there. Because if the negative had been there, then my vector would have rotated the other way. So this is the matrix you multiply a vector in 2 dimensions by to rotate it counterclockwise, whatever angle you want. So in this case, our matrix should be cosine of 3 pi over 4, negative sine of 3 pi over 4, sine of 3 pi over 4, and cosine of 3 pi over 4, which is going to be negative root 2 over 2, comma, negative, not comma, no commas in your matrices, negative root 2 over 2, root 2 over 2, negative root 2 over 2. Because cosine of pi over 4 is root 2 over 2, and 3 pi over 4 is the reference angle, is the angle with the reference angle pi over 4 in quadrant 2. And then we actually have to do what the problem says, right? It says use this matrix to rotate your vector. So then you actually have to multiply your vector by this matrix. So then A times our vector is going to be something you'd like to see maybe. Negative root 2 over 2. No commas, James. Negative root 2 over 2. Root 2 over 2. Negative root 2 over 2. And then we multiply that by the vector 2, 5, which is not pretty, but it's fine. This times this is negative root 2, and then this times this is this minus 5 root 2 over 2. And then down here we have this times this is just root 2, and that times that is again minus 5 root 2 over 2. That's a resulting vector. Ugh. It's not very nice, but that's what usually happens when you rotate a vector by some angle, is you get something that's typically not very nice. Yeah.
The negative, like, can we just figure out which one's negative, positive from that instead?
Well, I would say 2 pi would not be an excellent question because that'd just be wrote a full 360 degrees, which you get back. But if it was pi over 2, I would still probably write it out just because I don't know how to make sure I do it the right way. So even though I know from what I wrote up here, it should be this matrix here, I'd still double check just to be sure. Yeah, interesting. But yeah, but also I would say you probably could be fine if it was just pi over 2 writing this matrix. Yeah. And then there was one other one here about rotations as well. The reason I pointed that out is just because we never talked about rotation matrices at all. So I feel like it's on here. I should maybe mention it. There was one other thing I wanted to point out as well, which was question 15 from his list of many questions. And again, happy to address other things. I just am looking at things I made note of. It said, give an example of a 2x2, not matrix, but system of linear equations that has some number of solutions. And there's like 6 different things. And the first one is that has exactly 2 solutions. Now, here's what we should be thinking. When you're trying to write a 2x2 system of linear equations, you're really just writing the equations of 2 different lines. Oh, I'm sorry, it's a little blurry there. There we go. Can you have 2 lines that touch each other in exactly 2 points? You can't, well, not exact. When we say exactly, that means 2 and no more. That's not possible if they're both straight lines. If they touch in 2 points, they touch in all their points. So this is not possible, which he does write in the solutions, but I just feel like if I was writing a question like that, I would make sure that the students knew that that was an option. So just be aware, I guess. And then the other ones, since we're on the topic, if you're going to have no solutions, then those lines better be parallel. So one easy example would be something like x plus y equals 6 and x plus y equals 7. As long as the x's and the y's have the same coefficients or they're multiples of each other's coefficients, and the thing they're equal to are not multiples in the same way, they're not going to ever intersect. These are 2 parallel lines. Another example could be, I don't know, 2x minus 3y equals 5. Multiply each of these things by whatever number you like. I'm going to pick 7. And 14x minus 21y equals, multiply 5 by anything other than 7. Any number other than 35 right here will make it so these lines are parallel and never intersects. So not 35. Any other choice is fine. One solution is super easy. in that you just have to make sure the lines don't have the same slope. So one solution will look something like, I don't know, x plus 3y equals 5 and 2x minus y equals 7. Cool. They for sure intersect at one point, that without a doubt, because they're lines whose slopes are not the same. And for sure they're not the same because one of the coefficients is negative and none of the other ones are. So there's absolutely no way I could have messed up and gotten parallel lines here. D, infinitely many solutions. Now, this might feel like kind of a cop-out, but I think this is a totally valid answer. X plus 2y equals 6 is my first equation, and x plus 2y equals 6 is my second equation. You probably might not want to do that, but they didn't say you couldn't write, right? It's two equations, they're just the same equation. But I guess a more typical, better, safer choice would be multiplying this whole equation by any number you like, other than 0. So 3x plus 6y equals 18. This is probably a better way of thinking about that. Um, Interesting. I didn't even think about that. So I've been writing no, I guess no, that's not true. Yeah. I wasn't even thinking about this next part, but the next part is has only trivial solutions. Has only this is phrase I should say has only the zero solution, not zero solutions. That's kind of weird. But they mean that, well, it's all speaking towards the next quarter. What we're talking about here is having a homogeneous system where 0, 0 is your only solution versus a non-homogeneous system where 0, 0 is not your solution specifically. In fact, this here is an example, not this here. This here, we know those lines intersect. We know, well, I'm going to check here. Let's see, 0 for x and 0 for y. Yep, that is not where they intersect. It's not even a point on either of these lines. But if I want both lines to intersect at 0, 0, well, then I would do the following. So I want them to have only, I don't like the way this is written, have only the 0 solution, meaning x equal to 0 and y equal to 0 is our only solution. It should be something like x plus 2y equals 0 and 3x minus 4y equals 0. For sure, those are not the same line, and they both go through the origin. So the origin is the only place where they intersect each other. Do they go through the origin? If you plug in 0 for x and 0 for y, is it a solution? For sure is. And here too, for sure is. So both these lines have the origin. And since these are not the same line, they can only intersect in one point, and that has to be the one point. A lot of next quarter is looking at systems of two equations and two unknowns that intersect at the origin. So there's a reason why he's actually mentioning this. It's important for 17C. And then finally, the last one we've already actually answered, has no 0 solution. Whoops. This would be an answer to part F at all. F as well has no trivial solutions, no 0 solutions. So there is a solution, but it's not x equal to 0, y equal to 0, which is actually kind of atypical when you take 17C. Interesting. Okay. That was what I was looking at. What else should we talk about? I have an idea. Unless I'll wait a moment. Yes, over there first and then over there next. Sure. I can remember where I put it. There we go. Yeah. Number 4. Okay. Oh, that's number 3. All right, sure. I think this one might be this. I think this one might also be on his handout, but yes. It's a little bit long, but let's read the question and write down what's important. So assume that the population is divided into 4 age classes. So we have age 0, age 1, age 2, and age 3. And even though this problem isn't asking me to do it, I'm going to draw the matrix diagram because I think that's helpful. So I'm going to have my 0s, my 1s, my 2s, and my 3s. So assume the population is divided into 4 age classes and that 50% of the females age 0. So I'm going to read this whole sentence, I'm going to read it again. Because usually when it's talking about a fraction of an age group doing something, it's usually going to end with all survive. This fraction survives till next year. So this says 50% of females age 0, 40% of females age 1, and 30% of females age 2 survive until the end of the next breeding season. Meaning 50% of the zeros become 1-year-olds. 40% of the 1-year-olds, yes, become 2-year-olds. And 30% of the 2-year-olds become 3-year-olds. Great. Assume further that females age 2 have an average of 6.2 female offspring. So 2-year-olds are going to contribute 6.2 0-year-olds next year. And females age 3 have an average of 1.8 female offspring. Let's do this. And apparently 1-year-olds don't have any. Fine. If at time, so then they say at time t equal to 0, the population, which I might write as this vector, n of 0 is equal to 500 0-year-olds, 300 1-year-olds, 100 2-year-olds, and 10 3-year-olds. And the first question is, well, it's actually two questions in one, is find the Leslie matrix. We'll do that first. And the distribution at time t equal to 1. Meaning, find the Leslie matrix and then multiply that Leslie matrix by your population distribution at time 0 to get the population distribution at time 1. So, let's do the Leslie matrix. And how am I going to talk about this in a way that I like to think about it? Well, so I'm always thinking of my rows as the things that are going into that specific age category. So the first row should be all the things going into age 0. And there's two things. Age 0 isn't going into age 0. Age 1 isn't going into age 0. But age 2 is going into age 0 6.2 times. And age 3, 1.8 times. So this is I'm going to label it this way. This is into 0 and into 1 and into 2 and into 3. And the columns tell you where it's coming from. This is coming from 0, from 1, from 2, and from 3. Seems reasonable. So then for my second row, what's going into 1? Well, 0.5 times the 0-year-olds is going into 1 and nothing else. Into 2, we have 0.4 times the 1-year-old, so 0, 0.4, 0, 0. And then finally from 3, sorry, into 3, we have coming from 2, so 0.3. I will point out, because it is fairly typical, that when you have this situation where some fraction of each age group is surviving until the next year, you have this very, very typical thing where everything, I should say, you have non-zero entries directly below the main diagonal. Right there, and right there, all below that diagonal. It's very common if it's this sort of situation. So then we're going to take this matrix and we're going to multiply it by that. I wouldn't actually write it again if I was taking a test, but I'm not, so I'm going to write it again so you can see what I'm writing. Then we're going to multiply that by 500, 300, 110. Honestly, if you're running low on time, you might stop there. Move on to something else, because this shows that you know what you're supposed to do, even if you haven't actually done the multiplication. I might go one step further and at least write something like 0 times that, and then 6.2 times 300 plus 1.8 times, sorry, 6.2 times what? 100, not 300. And then 1.8 times 10. And then the second row is going to be 0.5 times 500. The third row is going to be 0.4 times 300. And the fourth row is going to be 0.3 times 100. I think you could safely leave it there, but if you have time, you should simplify it. You're going to get 620 plus 18. You're going to get half of 500. You're going to get 0.4 times 300, which is 120. 0.3 times 100, which is 30. That's good enough. And then, sure, the second part of this is kind of annoying, I feel like, but let's find the age distribution at t equal to 4. But it isn't saying you have to multiply it out. It's saying you can represent your answer as the power of a matrix multiplied by another matrix vector. You do not need to multiply it out. So what they're really trying to get you to say is, if we call this Leslie matrix L and this vector n of 0, then our answer to part B here, which I'm going to write up here, our answer to part B, we could very, very compactly write as L to the fourth power times n of 0. If you actually wanted to like write out the matrix and the vector, you probably could / should and write it as your big matrix to the fourth power times your n. But no one should be asking you at this juncture to actually calculate a matrix raised to a high power. Unless, oh, actually, I'll talk about that next. Unless, give me a second. I know there was a question over here, but I'm going to say one more thing before we go to the next question. So there is one kind of matrix that everyone here is very, very, very capable of multiplying by itself a lot of times. And that is called a diagonal matrix. A diagonal matrix looks like this. Sure. 5, 0, 0, -3. Or like this. 1, 0, 0, 0, 6, 0, 0, 0, -8. Anything that is not on the main diagonal has to be 0. You can also have zeros on the main diagonal as well. It's totally fine. You could have, this could be 1, 0, -8, and it would still be diagonal, as long as everything that's not on the main diagonal is 0. And here's what's cool about these matrices. They're really super duper easy to multiply by themselves. If you multiply this matrix, let's call this one A, let's call this one B. If I want to find A squared, that's going to be 5, 0, 0, -3 times 5, 0, 0, -3. And look what we get. We get 5 times 5, which is 5 squared. We get 5 times 0 plus 0 times -3, which is 0. We get 0 times 5 plus -3 times 0, which is also 0. And we get 0 times 0 plus -3 times -3, which is -3 squared. Which, yes, I know that's 25 and 9, but we're writing it this way to be kind of explicit. If I said a to the third, it's going to be that matrix, a squared, multiplied by another copy of A. And look what we get. We get 5 squared times 5 plus 0 times 0, which is 5 to the third. And 0 plus 0 is 0, and 0 plus 0 is 0, and -3 squared times -3 is -3 cubed. And so it shouldn't be surprising here that if I asked you to find like a to the 37th power, you wouldn't do this 37 times. You would say, hey, I see the pattern. That's going to be 5 to the 37th power, 0, 0, -3 to the 37th power. And that's true for any diagonal matrix. So for this matrix B here, if I want to know what B to the 10th power was, it would be, I'm not going to write 1 to the 10th. 1 to the 10th is 1. You should write 1. But any other number raised to a high power, just write it like that. So you're going to get 0, 0, 0, 6 to the 10th power, 0, 0, 0, -8 to the 10th power. So just FYI, those are, and there is a reason there, it's not just because he might ask you about this on your exam. There's actually a reason we care about these matrices as well, other than they multiply, well, actually because they multiply by themselves so nicely. Cool. What was your question? Oh, cool. All right, cool. Yeah. Mine or his? Mine. Let's take a look. Can I? Sure. Problem 1. We're going to let A be the matrix 1, 2, 0, 2, -1, 1. B is the matrix, the vector slash It's a vector and it's a matrix. 2, 1. And x is equal to x1, x2, x3. And the first part says, write the matrix equation AX equals B as a system of linear equations, not as matrices. So here's the wrong answer. This is not what they want me to do. To write it as 1, 2, 0, 2, negative 1, 1 times x1, x2, x3 equal to 2, 1. Although you could certainly start there to get what you want, because what they really want me to do is they really just want me to actually kind of multiply it out. So I'm going to take this row dotted with this column, and it's going to equal 2. So that's 1 times x1 plus 2 times x2 plus 0 times x3 equal to 2. And the second row with the first column is going to be 2 times x1 plus negative 1 times x2 plus 1 times x3 equals 1. And that is actually the answer they're looking for, because the question said to write the matrix as a system of linear equations, and that is what this is. Let's look at part B. Oh yeah, there's a typo. It's fine. So part B, find C equal to A times A transpose. So we already know what A is. A is just the matrix 1, 2, 0, 2, negative 1, 1. And then multiplying it by its own transpose, this first row becomes the transpose's first column. The second row becomes the transpose's second column. Now we're going to multiply it out. And I'm assuming we're going to get a diagonal matrix based on the next question, but let's see. Maybe I'm wrong. So let's see. This times that. Oh, no, sorry. I'm being silly. We get 1 plus 4 plus 0 is 5. And this with this is 2 minus 2 plus 0, which is 0. And same, it should be the same thing down here. 2 minus 2 plus 0 is 0. And then finally, second row, second column, 4 plus 1 is 6. And that was not wrong. Okay. And then question C asks us to find 4 things. One of them was a typo. So they ask us to find C inverse, C squared, C cubed, and that's supposed to say C to the 100th power, not C to the first 0, 0. I forgot some braces on that one. Okay, so C inverse should be the usual deal. C inverse, we're going to take our C matrix and we're going to say it's 1 over the determinant of C, and then we're going to interchange 5 and 6 and take the negative of the off things. But the negative of 0 is still 0. So I don't recommend writing negative 0. That feels real silly to me. I'm going to write this as 1 over, let's see, 30, because that's 5 times 6 minus 0 times 0. In fact, I should say that. 5 times 6 minus 0 times 0 times 6005. I do think here it's worth mentioning that if you actually distribute this, you get something kind of interesting. 1 over 30 times 6 is 1/5. And 1 over 30 times 5 is 1/6. And it is not at all a coincidence that since this matrix is diagonal, C to the negative 1 power actually is each entry to the negative 1 power. It's 5 to the negative 1 in that slot and 6 to the negative 1 in that slot. Kind of cool. So based on what we just did before, these other 3 are not too terrible at all. C squared, well, it's going to be 6005 squared. And we saw that for diagonal matrices, if you raise it to a power, you just raise the diagonal entries to that power. That's going to be 6 squared, 005 squared. And this, you should probably write as 360025. Similarly, C cubed is going to be 6 cubed, 005 cubed. 6 cubed is kind of big. Sure, 216, I think. And 5 cubed, we probably know. But certainly for the last one, C to the 100th power, you're expected just to write it as 6 to the 100th, 005 to the 100th. Yeah. Did I put them in the wrong? I put them in the wrong. I did. I'm so sorry. I put them in the wrong spot. Sorry. I was looking at this, not that. So these are both total. So yes, to your question, this should be a 5006 Good thing 5s and 6s turn into each other so easily. So that's a 5 squared, that's a 6 squared, and that should be not this. Thank you. Good call. Similarly here, this should be none of this and none of this. C cubed should be 5006 cubed, which is going to be 5 cubed, 006 cubed. And similarly, c to the 100th is going to be 5 to the 100th, 0. So it's a good reminder to be extra careful about what you're looking at when you're writing things down. It's very easy to make mistakes. I saw a hand back there. I'm assuming it was the same question. Yeah, okay. Okay. Oh, we only have 9 minutes. Wow, time flies. I think we should look at the first order linear differential equation because it's for sure one's going to show up on your exam. So let's say we're going to solve, this is problem 2 on the one I wrote. Y prime plus 2xy equal to x e to the negative 2x squared. Looks terrible. Looks really terrible. And also y of 0. Okay, so we're going to solve this in the usual way. What does this piece of information mean you have to do after you've solved it? Right, to do what? To solve for your constant c. So if you see an initial condition, it means, oh yeah, at the constants at the end, you have to solve for them. All right, so it's already written in the usual nice way. Great. So our integrating factor is going to be e to the integral of 2x, which is going to be e to the x squared. So then we're going to multiply everything by e to the x squared. So we're going to have e to the x squared times y prime plus e to the x squared times 2x times y equal to x times e to the negative 2x squared times e to the x squared. Two things. Thing one, you should always simplify this right-hand side as much as you can before you do anything else with it. So here, the e to the negative 2x squared times e to the x squared, they're going to add those powers together to get e to the negative x squared. So the right-hand side is going to become x times e to the negative x squared, which looks good because we know how to integrate that. It's going to be a pretty straightforward u substitution. The left-hand side, all you have to remember for the left-hand side after you've done this is it's always this times y, and then the derivative of that. So it's whatever your mu of x was, it was e to the x squared times y, the derivative of that product. Every single time. No exceptions. Question. Oh, you're not. Good call. Thank you. And then you rewrite it by basically just saying you imagine you were anti-differentiating both sides and say, cool, the e to the x squared times y equals the antiderivative of x e to the negative x squared dx. I personally probably would like do this integral before I brought this over, but either way is fine. To do this integral here, we're going to let u equal negative x squared. Du is negative 2x dx. So negative 1/2 du is equal to x dx. So the integral of x e to the negative x squared dx is going to become the integral of my x dx gets replaced with negative 1/2 du. So negative 1/2 times du. And my e to the negative x squared is going to become e to the u. And that's real easy to integrate. It's negative 1/2 e to the u plus c, which is negative 1/2 e to the negative x squared plus c. That's what that right-hand side is. Whoops, you can't see that. Sorry. So then we say, great, our e to the x squared times y is equal to negative 1/2 e to the negative x squared plus c. And then you can either divide both sides by e to the x squared or multiply both sides by e to the negative x squared. It's the same difference, which is just whatever you prefer. I'd probably multiply. So I'm going to say that y is equal to e to the negative x squared times negative 1/2 e to the negative x squared plus c. And should I distribute that? I don't know. Kind of up to you. I would probably distribute it because I don't know. That's what I like to do. So distributing that, we get that y is equal to negative 1/2 e to the negative x squared times e to the negative x squared. We add those powers and get e to the negative 2x squared plus c times e to the negative x squared. And now we're going to use our initial condition that y of 0 is equal to 3 over 2 to solve for c. So y is 3 over 2 and x is 0. So you get negative 1/2 times e to the 0 plus c times e to the 0. Oh, that works out great. So then you have 3/2 equals negative 1/2 plus c. So 3/2 plus 1/2 is 2 equal to c. Don't stop there. Technically, there's one more thing you have to do, which is go back and rewrite your solution with the c value plugged in. So taking this and this, we're going to get that our actual final solution is going to be negative 1/2 e to the negative 2x squared plus 2 e to the negative x squared. Cool. All right. Yes. Yes, that's the final answer. Now, a follow-up question could be something like, no, that's not a good example, James. No, that's not good at all. I would mention I wouldn't be terribly surprised if there was some sort of tank problem on your test where you had stuff going into it. So I would be what's the word I'm looking for? I think it's most likely that if there's a tank problem on your test, which I think there will be, that it'll probably be a setting up and not a solving problem. And it will probably also have the situation where the volume going in is different than the volume going out. So let's do that with our last 3 minutes here. So let's say we have a situation, we have a tank that holds, I don't know, let's say 100 gallons of fluid with, sure, 12 pounds of salt dissolved. We are adding a solution with a concentration of 3 pounds of salt per gallon at a rate of 3 gallons per minute. I don't like using 3 again, at a rate of 5 gallons per minute, and draining the tank at a rate of 9 gallons per minute. Set up, but do not solve the differential equation. I'm going to say the differential equation and the initial condition for the amount of salt. Okay, it's not terrible. So ds dt, the rate of change of salt, is equal to the salt going in minus the salt going out. The salt going in is usually pretty easy. The salt going in is going to be the concentration going in, 3 pounds per gallon, times the rate it's going in at, which is 5 gallons per minute. Or in other words, we're adding 15 pounds of salt every minute. The salt going out is always the more complicated part. It's the rate going out, which is not terrible, 9 gallons per minute. And the concentration going out, which is always the challenging part. But not really. The concentration going out is always the amount of salt in the tank, which we are calling S of t. So it's the amount of salt in the tank at time t. Divided by the volume of the tank at time t. And in this problem, the volume is changing because we're putting in and taking out a different amount of volume every minute. So we're starting off with 100 gallons of volume, and then let's see, we're adding 5 gallons every minute, but we're losing 9 gallons every minute. So every minute we are losing a net of 4 gallons. So we're subtracting 4t. And then you could rewrite it if you wanted to without any of the units. So it would be equal to 15 minus 9 S of t over 100 minus 4t. That would be your differential equation without any of the units. If you did get asked to solve this, you would have to use a first order linear differential equation. There was no other way to do it. And then we would also need the initial condition, which is super easy. It's S of 0 equals 12. All right. I'll see you on Monday. I'll see some of you after your test and some of you before your test. So good luck if I haven't seen you, and good luck if I have. All right.
Want to quick
Yeah.
clarification on something?
Sure.
I'll let you finish that first.
Let me stop this here.